actually go over a couple of things, referencing the questions about formulas and that kind of thing. I want to show you some of the things that you have in your head are actually on this formula chart. They look a little cryptic, so I want to reference that. But first thing is, I got this question some today, and I wanted to just really solidify this. I had questions on how do you tell the difference between Z versus t-test and when you do which. So, here it is. For sure, if you have a proportion problem, then you always use the Z-scores, okay? You always reference a Z-score. And that means that it is the actual real standard normal model. So then when you do computations, you're going to be doing norm CDF from Z to Z. There's no degrees of freedom for the normal model because it is just the normal model. And then inverse norm, if you're finding a critical value, your Z star, okay, of one tail, no degrees of freedom. That's kind of when you're finding that critical value. Okay. All right. But for means, you have an option. For means, there's two things that could happen, and we've already referenced this. If you have the standard deviation of the population, which rarely happens, I have not shown you this, I have not had you do this, and I will tell you that it's not going to be on the test tomorrow just because I'm not throwing that little, that little thing in there yet, okay? So, but when that does, then you get to do those problems just like the proportion ones, where you do a Z-score. It is completely normal, not nearly normal, and you do your inverse norm and your norm CDF and all that kind of stuff. But what we have had for means this chapter is when we have only been given the standard deviation of the sample. So that is when we use these t-distributions because they are more varied. Okay, we're using our t-distributions, which are more varied than the standard normal curve. That's why we call them nearly normal. So when we are doing computation, we're doing our t-CDF from the lower t to the higher t, because these are from least to greatest. And again, what's this degrees of freedom important for? Notating which curve, which t-curve to compute off of. Okay. And then, of course, to get a critical value, you're doing inverse t of one tail common degrees of freedom. Okay. All right, so with all of that being said, now let me show you the formulas and for interval and your Z-scores or your T-scores, where they're located on your formula chart. So I want you to envision the little yellow formula charts. Oh, it's on this. Okay, the yellow formula charts I give you, you have one in your notebook that's bright orange, and then I don't know what color. I think usually the AP packets are green, so whatever. This picture will be one of your formula charts on the AP test, so you can use anything on it. This is the front. This is the back. This is what I'm going to talk about today. You may or may not have known, but the Z-score and the T-score are on this thing. They're just written with words, and so they're a little more cryptic. So, for example, see this? Standardized test statistic. I'm going to first do this standardized test statistic and this confidence interval for proportions. Okay, so let's do that first. So we know for proportions, do we find a T-score or a Z-score? Okay, we're going to find our Z-score. Okay, that equals. See this formula here? It actually is supposed to have a line here. This is, it just didn't show up on this copy. So, the statistic is your sample statistic. So, for proportions, it's that p-hat that you got from your sample. Minus this parameter is the population true p that is hypothesized. Over the standard deviation of the statistic. Well, guess what? Look at here. Standard deviation of statistic for proportions, okay, is right here. You asked me where all this stuff is on the formula chart and everything, and I'm showing you this here, okay? So right here, The bottom, of course, is the P times 1 minus P over Rn. Okay, so that's the z-score formula. It actually is written there. It's just kind of more cryptic because it's in vocabulary words instead of symbols. Okay, so now let's do the confidence interval for the proportions. It also is here. It is the statistic, which for proportions is going to be what? Your p hat, plus or minus, critical value. What's that notated as? Okay, we do a CV, but I mean, I think technically whenever you go looking at it and stuff, it's a Z star. And how do you compute that? That's your inverse norm of 1 tail based on how confident you are. For example, 95% confidence puts 0.025 in 1 tail, and so on, okay? Times this standard deviation for the statistic, which once again for proportions is your square root of P, 1 minus P over N. Now, FYI, on an interval, do you remember that you actually don't have true P? Because that's what you're estimating. So in the event you don't have true P, you go to what?
0.5.
P hat first. If you don't have true P, you go to P hat first, and then only in the dire emergencies, if you don't have P or P hat, that's when you use 0.5. And I think that there is one on that multiple choice stuff I gave you to practice with the 0.5 thing.
If you don't have the P hat, you have to find whole confidence. If you don't have
Ah, that's true. That's true. Yeah, so they would have had to given you this. It was probably something else where maybe they were asking you to estimate N. That would have been the case. And so they said, I want them. By the way, what is this piece here? This entire plus minus section of the interval is the what? Good. So if in the event that, say, maybe you were saying, what's the sample size needed for this size margin of error, then that might be an instance where they don't give you the p hat. Okay, good point. So margin of error, you think you need a stamp for that? Okay, I'll think about it because you just need to make up some, you know, some good stuff for whatever you were just messing with all those other questions. Okay. Raccoon, whatever. Okay. You got to dig yourself back out of a hole first. Okay, so now let's do this for t distributions. Okay, here we go. The test statistic t equals. What would the statistic be here? What symbol goes here?
P minus P hat, or P hat minus P.
We are in t distributions now. X bar for the sample mean minus the parameter mean, which is mu, over the standard deviation of the statistic, which is this. However, you know we're going to be having this standard deviation of the sample, most likely. Okay? Okay, so there, see, on the formula chart is your formula for the t distribution by hand. Okay, and so now let's do the interval. Statistic for this interval is what? X bar, that is your sample mean. Plus or minus, critical value is, that's your T star. And so what I'm going to do for that is, how will I compute it? Inverse T of 1 tail based on how confident, and then what else? Degrees of freedom. Okay? All right, and then finally times that standard deviation of the statistic. Okay. All right, and now you have just told me that this component here is your margin of error. So, let's talk about that for a second.
If you don't have X bar.
You mean as far as like estimating the sample on this one? Or what? Estimating it? That's a good point. This is the first year that I did not have us estimate an N if you in a t distribution, because in order to estimate an N, you have to have an N. You know, in order to estimate an N, you have to have an N. So that's why it's kind of like very difficult and not a very exact science, and that they don't do that on AP. Okay, so I did confirm. You see what I'm saying? Because you would need this in here, but you're estimating in, so how can we do that? All right, so let's go into this, though, with number 5 on your review. Hopefully you've already looked at some of these ones on the review with the pink paper I've given you, but let's look over at number 5. Okay? Now, I will tell you I got some questions on number 4. Here's the questions I have gotten today on number 4. It was, if you just have this list of information, how am I getting this thing right here, standard deviation for that list? Okay, how do you get the standard deviation for a sample list of data? That's when you put it into a list and you compute count over to stats, one variable stats, or sorry, stat over to count, one variable stats in your calculator. When you put this in, it will give you all of the information you need to know about your list. All right, including this standard deviation. Okay, so that's one thing I've gotten. And also, as you can see on number 4, see, I am showing this formula by hand because this was just a one sample t-test for means. Okay, so I'm wanting you to still be practiced in that and not just rely on your calculator. All right, now here we are to this number 5. What things change the size of an interval? 2 things. The size of your sample is correct. What else? What? Your confidence level. Okay. So, as you can see, for example, from this margin of error, here's your critical value. So, if you look at part A, the confidence is the same. So, what's different is the sample size. N is 25 or 75, and so if I'm going to make this bigger, then that makes your N smaller. Because N going down makes your standard deviation going up. And if this is a bigger number, then your margin of error is bigger. Okay. And B addresses the other part. B addresses if these N is the same. So both of these sample sizes were, I think, 50 where I marked them out. But the critical value is different because we had a 90% confidence versus 99. So just think of this picture here, because a 99% confidence will encompass bigger critical values, so more data, bigger interval. Okay, so that's how you tell the difference on that one. Questions there? Okay. Any questions on the 1 through 4 that I skipped over that you have checked?
What was which one was the number 3? I think that was a proportion.
Number 3 is a 2 proportion, so you are allowed to do that one in the calculator. So it looked like this. Keep in mind that your large enough conditions are the greater than or equal to 10s for proportions. It is a 2 sample z-test, so see, the exact normal curve applies, normal model applies. And then I was able to do this in my calculator. Do I have degrees of freedom for proportions? No. No degrees of freedom because it's the exact curve. Okay, and so on. Number 6, the only question I got on that is how did I know this one was paired? And the answer is because, each subject took 2 tests. So, I mean, it was 1 person, 2 tests, so there's really only 1 sample. Okay, that's the only question I've gotten on that one. Next. Go ahead. Number 7, I have an incorrect p-value on your pink papers, your pink answer keys. So let's talk about that. Number 7 is a 1 proportion problem. So I was looking to see that you can actually do the z computations by hand and that you norm CDF'd for 1 tail. Now, if you had done this in your calculator, it automatically plops out the answer for 2 tails if you put a not equal to in it. But when I did this by hand, I errored because this number is just for 1 tail, and since my hypothesis has a 2-tail alternative, then I needed to multiply this number by 2, so the p-value is 0.00765, which still actually gives me the same decision, so that was good. All right, now, next question. Am I there yet? Okay. 8, I don't think I had any questions on that one. The thing I wanted to point out on 9 and 10 is to please not forget that when you make an interval, you need parameter and assumptions. You cannot leave off the P and the A of the panic model and just do this part right here. Okay, and just do the interval. Actually, you might even leave off the N. You do not leave those off. Now, this part here is not required, but I do want to see this when you have one sample. Remember, I'm forcing you to still understand all the components to one sample formula.
We can check with the calculator.
Absolutely check with the calculator. That's a good idea. Okay? The reason I still make you do this is for those problems like on the multiple choices that have you know the formula outline, okay? So there's a reason for that. It's not just me being mean, although I like to be. Now, when you get down here to number 11, please notice that they gave you the variance. So that's the standard deviation squared. You had to take the square root of it to get the standard deviation of the sample. Now, I thought this problem was a little messed up in that I couldn't tell if it wanted me to do a z-curve or not. Because technically, right there, that's kind of notating the standard deviation of the population since it has a sigma. So I think it's possible. I don't know. I can't remember if the person who made these problems wanted this as their answer, but I should fix that notation probably. I went ahead and did the sample T stuff because that's what I'm going to have for you. Okay, number 12, I boo-booed. It's actually in as 9. Now, let's address this problem with these histograms. Okay, so I was concerned and perplexed with these histograms because neither one of them. Now, unimodal, yeah, I can see unimodal. So I can see unimodal. And I can see no outliers. Okay, because just one little bend skip probably isn't enough to say it's an outlier. But to me, the symmetry is an issue. I'm thinking, hello, that is pretty much not symmetric, so I'm not liking it at all. So you need to notate that, but don't ever stop on AP. Now, you certainly can, unless it is like crazy obvious, or the question is saying something like, are the conditions for inference met? Okay, then that is an indication they're giving you an out that this might not be met, and so you could be stopping, okay? But, okay, so if this is your job in real life, then when you get to this point right here, I would go, when you get and you see these messed up histograms, I'd go to my boss and I'd say, look at this problem. Do you really want me to continue? Okay, because I'm not going to feel very confident about my conclusion.
But if you had the job of preventing forest fires, would you be like Smokey the Bear?
Probably what would happen is if I was like Smokey the Bear, okay, and this was a really important thing in wildlife, and I was the head of the Wildlife Commission in the state of Texas or whatever, okay, and this was a really big deal. I'm just speculating here because I don't know. I would probably want more than just a sample of 10 or 9 to base my decision on. I would probably collect more data and see if more data still makes the shape of the population unclear. Okay, so I would want to have more data to make a final decision as to whether or not I take this information or not. Okay.
Oh,
Yes.
if that's bad, and then it's not even random, shouldn't that halt your operation?
Well, it not being random or representative, if it's not representative, then from the get-go, you're not doing it. Because why should you make any conclusion on something that's not representative of the population? Period. I mean, that's the quickest way to stop it. So that always has to be assumed. I mean, you have to go with something that it is reasonable that this is representative, or else, boom, you're done. Okay? All right. This one is just the thing there going on. All right. Here we go. This is where most of our questions come up. Okay, this is the Montagues and the Capulets and their propensity to fall in love. And so here we are talking about their average score on whatever test it was that they took. Okay. So, you know, you need to be aware that on some of these problems, even that problem that was about the errors, is it on the, oh, it's on this page. Number 16, about the errors. I don't see how you can do these problems without thinking about what the hypothesis statements are. Okay, so be aware that you might have to envision what these hypothesis statements are, even if it's not specifically asking you to state those. So, for example, on this Montague and Capulet problem, I determined that the null hypothesis is probably that the average for the Montagues is the same as the average for the Capulets, and then it's asking for a difference, so the alternative would be two-tailed. Okay, so then from that, the key to solve this problem is your t-score. And so, with a t-score of 1.75, what do you know about standard deviations away from the mean and being unusual? Is 1.75 going to be a very unusual sample? No, it is not at all. For t's, for sure. So 1.75 is well within 2 standard deviations. So I am not concerned that my sample is a whacked out, way outside sample that calls into question the null hypothesis. So, in summary, since this test is just 1.75, I would not expect to get a really small p-value. That would cause me to reject a null, so therefore I'm going to fail to reject. Therefore, there is the Capulets, actually I marked over the question, the Capulets are not significantly different from the Montagues. Yes?
Are the parameters of 2 standard deviations on a z-curve the same for a t-curve?
If you're asking, okay, this is actually a good thought. Here's the normal curve. Okay, and so if I go, say this is a z-score of 2, okay, then I'm going to have 2.5% out here. This is an approximation. Okay, but on a t-curve is more varied. So let's think about this. Okay, which I heard that coming out here. So a t-curve is going to actually have more in the tails. So even if you were at 2, this area in the tail of a t-curve, I mean, I'm exaggerating here, is going to be larger than what it was in the normal curve of 2.5%. So certainly at 1.75, there's going to be way more than that 2.5% for sure, okay? So that's why you know you're really, really safe. All right, so there you go. That was how I came up with that decision. C was pretty straightforward just from your number 15 was pretty straightforward just from your basic understanding. I had somebody ask me earlier about this because they had forgotten about it and hadn't seen it in a while, and the question was, are there going to be any error questions on the test? And my answer is, maybe. I don't know. So don't forget this stuff. So here's the type 1 and type 2 error, which you know the foundational concepts of. All right, so you can read that, and I don't think I really had any questions on that. So let's go on to number 17 is the song about the p-value. It's the probability, okay? And Brown Eyed Girl song. Y'all good? Need to sing it? We're good? Okay. So here we go, number 18. 90% confidence interval is this. Here is the key to this problem. The key to this problem, because see, once again, I am thinking about what the null in the alternative hypothesis would be. Okay, so my null is that the average is 86. So what happens is, if I see that this 86 is not in my interval, then I think when I go run a test, I'm probably going to reject that null hypothesis. So that was the key to notice, that 86 is not in the interval. So since it's not, I anticipate that when I run a test, I get a p-value small enough, and I'd reject the null. 19 was just 70% confidence, which means that's what's in the middle. So therefore, this critical value is inverse t of 1 tail. I think technically you have 2 critical values when it asks you for something like that. And number 20, I'm not going over too much. This problem here, I'm actually going to reference more in depth on the next page. So let's just hold off if you have a question on that. 21, your sample is right in the middle. Okay, 22, we've done this before. You remember that if your sample is in the rejection region for 10%, then it is definitely in this rejection region for 20%. The question, is it in the rejection region for 5%? And that answer is not necessarily. It might be down there, but it could be here. And in that case, it's not in the 5% rejection region. Okay, we've had that before. I think there's even a multiple choice one on there that you have in your hand. All right, last idea. Here it is. Okay, this one is saying that the sample size is 15, so our degrees of freedom is 14, and the alpha is 10%. So the key to these problems is this, the tails. Since this is indicating 1 tail, then I know that this 10%, the entire 10%, is located in this upper tail. Okay? So then to find this critical value right here, this t star, I'm going to inverse t of the area below, 0.9, 14 degrees of freedom. And that's how I get my 1.35. C is almost identical, it's just this lower tail. So since this here is the lower tail and the entire 10% is in the lower tail, it's the same symmetrical critical value, but negative 1.35 because it's inverse t of that lower 10%. Okay. B and the 2 tails is where it differs. Because if you have 2 tails, then the 10% is split between those 2 tails, and you have 2 critical values. The lower one at inverse t of 1 tail, and the upper one. Okay? Now, this question was not asked, but it's an extension. How confident are you going to be for part A and part C? They're the same. And that would be what's in the middle. So see this right here? If this were a confidence question about what level of confidence do you have, part A and part C has 80% confidence because they put 10% in this 1 tail. So by symmetry, you have the other 10% in this lower tail, leaving 80% in the middle. Okay? But since on part B, the 10% is split between here and here, then that's a total of 10% between the 2 tails, giving you 90% in the middle. So that's a 90% confidence of how much you have there. Okay. Questions there? All right, then the final 24 and 25 are about this being a problem about the difference. So since this is about the difference, then I'm interested in if 0 is in the interval. And so as you can see on 24, 0 is not in the interval, so I am confident of an actual difference. Because here, if 0 is in the interval, there could be 0 difference. That's what's happening. Am I saying there is? But no. But there could be 0 difference if it's in the interval. Done. Okay. So that's all I have to say about that. Any other questions? Okay. Ta-da. Yeah, Byron, what you got?